Hello, I'm Amitov. Uh, this is tinygrad-verilog. This is a project. I worked on it. You can see by timestamps here, like a week ago. And then I had like, ah, you don't need to know all the context right now. Basically, I'm trying to implement tinygrad and verilog. Pretty much, that's what it says on the tin. Um, I just want to sort of finish it now. And I thought uh, recording it might be a good idea. So let's get started. Already have some stuff made already. So let me just go through this adder. This is simple. ChatGPT made this so that I could figure out how to use Verilog. 8-bit adder. So input starts at bit 0 to bit 8. So that'd be 1, 2, 4, 8, 16, 32, 64, 128. So you could store up to 255 in this, and then 9-bit output. In case it like overflows, then we have that extra bit, so you can be like, oh no, it overflowed. Yeah. Um. So there's that. Uh. Next up, I think. Okay, let me look at this architecture file here. Okay, this is like outdated, I think. Um, Here. This is Mac unit multiply accumulate. So um, this is where Verilog starts to get interesting. So you can pass in a parameter. What this is like when I'm making, because you got to remember this is all like actual hardware. Um, so this is like we're defining how many inputs we're giving it. In this, like we default to 4 just because I don't know, but you can imagine this as like um just like let's say we have some black box called the multiply accumulate units. So we would get these are a bunch of input wires. So in this case, this is 2x weight pairs. Now, even though these look like 4 wires here, because we're using 16-bit numbers, that would actually be 4 times 16, which is 64. But I don't really want to draw 64 wires, so just it's implied that these are 16 wires. So these in like the default one, because this has two XY pairs, it would be MAC with 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 input wires. So these are our inputs right here. Um, and then we have some more input wires. So uh, here. Just pretend that's symmetrical. We have the clock wire. So this is what like every time we get fed in a new pair of inputs, they also increment the clock by one. There's clock, there's the clock wire, there's the reset wire. So the reset wire also pretty much does what it says on the tin. If we pass in true, then whatever like we've accumulated up to that point will just get flushed and we'll start anew with like all zeros. And finally, the start wire. So to be clear, these are actually one wire each, but all of these up here are 16 wires because one wire per bit. Um, if you bits because bits are just zero and one, so you can represent a bit of information in a wire by just either sending electricity through that wire or not sending electricity through that wire. If you don't send electricity through that wire, it's zero, else it's a one. Cool. So the outputs are the accumulated results and uh, done. So basically, we check if I actually forget how this works. So these are registers, which I think means that they can be changed on the fly. Here, register versus wire verilog. Here, Stack Overflow. Um, Used for connecting different elements treated as physical wire. Don't necessarily correspond to physical registers. Represent data storage. Obtain their value till the next value is assigned to them. Synthesize to FF latch combinatorials. Um, wire elements. Assume I have two codes. Cool, cool. Okay, so yeah, we have another register to count how many values we've accumulated. This is just taking, this is just figuring out how many bits we need to hold the count. This minus one is because we start at zero, and then this takes uh log 2 n is equal to counts. So that would mean that so that's how many times uh, x to the y is equal to z. So then mm, log, so if x to the y is equal to z, then where is, here's my phone. Um, well, I guess here. I think I just hit the lock button by accident. That's weird. Uh, Here. Okay, I can remember this. Log 2 of 8 is equal to 3. I remember that. And, okay, so this is how many times you have to multiply 2 together to get n. So the reason, yeah, okay. Oh, you can't actually see my, that's odd. Um, Remove, yes. Add, screen capture, okay. Built-in display. Move that there. Okay, now you can see everything. Cool. So, we have our multiplier over here. Um, this is another Verilog module we have. Fixed mul. So this takes in two 16-bit inputs. So 8 integer bits, 8 fraction bits, and then multiplies them together, and then we drop the top 8 and bottom 8 bits. Yeah. This is fine, like, for our purposes because uh model weights are usually like tiny, and this is good for like -128 to 127. Yeah. So basically we multiply our inputs by our weights, and then the result of that is fed into our product var. So then this is the main state machine. So the way this works, like in when we're actually running this, this is a single module. We have our multiply accumulate units, and then around that we have the test bench. So basically, in the test bench, we have a clock signal which basically oscillates between 0 and 1, like that. And now this is fed into this multiply accumulate unit. So what this is doing on pause edge clock, saying if we're at, you know, this or this or this, then then run this, run this again. The reason we have like it oscillate is because otherwise the signals wouldn't have time to propagate. So like if you imagine inside the multiply accumulates, I have so this is if reset, so we can ignore that. Load first product. Okay. So basically what we're doing here is we're setting accumulate to be equal to accumulate plus product. So at every for at every clock cycle, the test bench is feeding in another pair of inputs and weights, and um we one second, I'm gonna go to the bathroom. I have returned. So um on every clock cycle we we add the product and the accumulate and what's already been accumulated into the accumulate. And the reason we need um, this period right here, this is when multiply happens. So in between, yeah, in between each edge, that's when the electricity flows through the multiply circuit. So then um, on every clock cycle, yeah, we are accumulating the product. And let's look at the test bench. Shall we here? So this is the clock, reset and start registers. Here are the inputs and the outputs. Over here, we're just instantiating this. So you can see here all the inputs and parameters match. And then over here, we have the clock generation. So this tilde right here is a not operator. So every 10 seconds, it sets clock to be equal to not clock, which basically means if clock is 0, it sets it to 1. If clock is 1, it sets 0, which gives us that oscillating pattern. Um, these are some helper functions that just converts our weird formats to an integer or an integer to our weird formats. And here is, so over here we just have an array of x's and weights. And this is what we will use to loop through each of the inputs. So our inputs are 1, 2, 3, and 4, and our weights are all just 0.5. So we start, clock is equal to 0, reset is equal to 1, start is equal to 0, x is equal to 0. So this is in case, I actually don't know why we had this reset here. So after 20 nanoseconds, set reset to 0, wait another 10 nanoseconds, and then, yeah, we start. Well, also, up here says 10 nanoseconds period. This is actually incorrect. This is 5 nanoseconds. I do not know why that's come to us wrong. So over here we set the start to 0. So you can imagine our modules already been instantiated and it has all its wires hooked up. And then basically from the test bench, we are setting that to 1, and now this is flowing into the multiply accumulate, and then the multiply accumulate sees this, says, oh wait, I am supposed to do something here. And what it's supposed to do is all of this stuff. So then it also sets x equal to the first element, 1, y equal to, sorry, w equal to the first value of w. We wait another 10 seconds, set start to 0, and then loop through the remaining values and feed them in one by one. After 20 nanoseconds, we display the results. Yeah, so that's how our multiply accumulate works here. So from there, we also have our ReLU. So So what this is doing is what our ReLU does is basically if um, if you don't know, like a ReLU is called is the expanded form of a ReLU is rectified linear unit. So if we imagine we have like Cartesian plane, imagine that that line's straight and that that line's also straight, and then we have, so this is, let this be y is equal to x. If we were to apply a ReLU to this function, once y crosses below 0, y is just equal to 0. So this is our activation function. So now, what this is doing is y15, this is just checking the sign. So if it's negative, it sets it to 0, else it sets it to y. And then, yeah, the output is the activation. So it sets that wire to that value, and then that wire is the same wire. Uh, and then if we go back to, yeah, now we can head to uh, activation. So we are given the weight, the bias, and the start input wire again, and our outputs are the activation and it's done. So basically, weight, this right here, weight product, this is the input times the weight. So our pre-activation is weight product plus the bias, um, because uh, y, like before the activation, y is just equal to wx plus b. Fun fact, um, this is without this activation function, a single like a single neuron is just a line. Isn't that cool? Because this is just y, right? Sorry, m. This is the slope of the function, and this is the y-intercept. Yeah, I know. That is just sort of interesting. And then this right here is the module we were just looking at earlier. And yeah, so that is our activation. And from there, we have our neuron. So we are give over here we have those same parameters for by default again, and then our clock wire, our start wire, our input wire X, our weight wire, our bias wire, and then our output activation wire and output done wire. So this is accumulate, reset, and then are we done the multiply accumulate. So we assign reset to 0, and then over here we are just setting all our inputs, um, setting all our inputs, parameters, all that, and then basically the way that this neuron is run is that um, the test bench feeds it on every clock cycle a new um, XW pair, and so this is every clock cycle. We have a bias, which is fed in just once at the beginning, and then um, you can see here we have our activation module from earlier, and the start is just whether or not this multiply accumulate module is done. So from there we have a layer. So um, this is where things get like nicer. So you imagine like I have a single neuron and that takes in multiple um, da, da, da. This takes in n inputs and returns one output. So now the way we have this running is that it also gets and fed n weights because it has one weight for every input. Now if we zoom out a bit, so that now we're not looking at any individual neuron, but instead a layer of neurons. So each input is fed to each neuron. So each neuron gets the same n inputs. Now, the way we've implemented it, the weights are fed in to the layer. We feed in call say call the number of neurons in a layer m. We feed in m weights with every clock cycle. Then those get distributed to each of the neurons, and each of the neurons runs that multiply accumulates, and we give each of the neurons their biases at the beginning, at the initialization, and then I think it'll be more intuitive if I just walk you through the code. So our input wires, you can see n times 16. So this is this n right here is the number of imp like the number of inputs to the layer. Then over here, our weights is m times n because for each of our M neurons, we have N weights. We have, so to put that more clearly, for each of our M neurons in the layer, each of them has one weight for each of the N inputs. So M times N. Then we multiply 16 because we have 16-bit numbers. Subtract by 1 to avoid off by 1 errors. And yeah. Then we have biases, which is m by m times 16, and the uh m times 16. So we have, yeah, each neuron has its own bias, and that bias is applied to each of, well, to say it's applied to each of the neurons inputs is a bit misleading. The way like this works is for a neuron, we multiply like we take the sum of uh I don't know, I equals 0, n. This is the, remember, this is the number of inputs. So x I times weight I, and then we add b to this. I think. Let's look at the code over here. So we have an m, but we have an m sized array of activations. Again, because we have one activation for each of our m neurons. This is for iterating, and then yeah, this is over here. We procedurally, I don't think that's the right word. We this is a special type of for loop in that like it's not dictating how the program should run at runtime. It's dictating how the program, like how the hardware should compile. So because we want the number of neurons to be different depending on the number of neurons we specify, we use this for loop. So this stuff over here is just to allocate to each neuron uh it's like its specific, its required inputs. So this is actually incorrect right now. Um because what we're, I think it's incorrect. Yes, because you can see we have I in here, which means which implies that every neuron is getting a different subset of the inputs, but that's just not true. We Each neuron gets the same inputs at the same time. So we can add another wire uh, signs x um, 15 0 x val. Indentation is weird. Is that because I'm, ah, okay, there, everything should be formatted correctly now. The only thing I'm not sure of is if this is a valid way to have, um, like, if this is a valid way to have, neuron names. Here, let me, uh, how to use for loop to synthesize modules verilog. Here, here, um, here. Let me ask ChatGPT actually. This is for chat DeepSeek. Hey DeepSeek, is the way I'm naming each of the separately instantiated neuron modules valid? Okay. Um, Interesting. Okay. Here, so I learned something new today. This has to be gen bar. Then this has to be in a generates. So generates and generates. And we should be able to, uh, can I just do this? And yes, I can. Amazing. So over here, this will be X val. So the reason I'm feeding in all of the inputs and weights and biases all at once is because then I think it will make it easier when it will make it easier when making the test bench because I can just define all of my inputs, weights, and biases all at the beginning, and then basically say, here you go, knock yourself out to the module, have it, give it like a clock signal, and then wait until I get the done output. So here, let me make sure that these are allocated correctly. This is uh, to here. So 16 times n times I plus 1 minus 1 times 16 times n times I. I feel there's no way that there's not an off by 1 error hidden here. So let's, I don't know, just calculate this, hand crank this with some numbers. Let n equal 2, let's m equal to, yeah, and that's all of the values you need. So what we're doing here is let's say for um the second we're generating the second module. So 16 times n, that's an m. 16 times n times I plus 1 minus 1 to 16 times n times I. So we can copy this, paste this. Let's replace I with 1. Replace I with 1 and n with 2. So if we've done this correctly, then the difference between these two values should be, I think, just 16, 16 bits. If we, oh wait, did I? Yeah. If I jump back to neuron.b, yes, because this takes in a 16 bits wire. So this is equal to here 2, 2. So this is equal to 32 times 2 minus 1 to just 32, which is equal to 63, 32. That's wrong. This is it 32 bits? 31 bits. Yeah. Okay. Um, we have to figure out why this is. So the way I'm imagining this array being part, well, this array really is just like a big long number. But the way I imagine this big long number being partitioned is that you have, because we're generating it, because we're basically chunking the weights per actually I think it makes more sense to not deal with this sort of like, you know, um splitting nonsense and instead just have um we'll have like the array be split up like one row is weights for the first input to the first neuron, weights from the first input to the second neuron, etc. Weight from the first input to the mth neuron, and then over here we'd have, and then what we can do is we can store each row in W files, chunk, then assign when generating each module, we can assign each of them a certain number of bits from that number, and then when we're actually running the training, we can basically just every time we finish an epic, no, not an epic. Uh, once we finish a batch, uh, a single input, we can just set wvals to be equal to that plus n, right? So the start number gets bumped up by n and the n number gets bumped up by n. So if we were to implement that, we'd need an m times, yeah, because we need for every, we need a 16-bit number for every neuron to 0 w vals. And then if we go back over here, instead of doing these shenanigans, we can just say it's equal to I plus 1 times 16 minus 1 to I times 16. So then on the 0th, yeah, that checks out. Then biases, that looks good as well. And yeah, so, oh, I did not, it should be W vals. What? Do we have an we do not need these parentheses, I believe. Yep, okay. So, once we're done generating, let me add the ends module here. So, then we need the always block, right? So, I don't actually remember how to do this, so mac.b here, always at pause edge clk begin. Holy smokes. Can we invent this? Something's up. I don't know what. Module layer. That? No. I swear something looks weird here. Comma, comma. Hopefully it's nothing. So, I don't know why the indentation is giving me so verilog mode. So this, and here. Oh, we're missing closing parentheses. Okay, then ends generate. And then we have the always look. There, okay. So, um, I guess if start begin, so what we'd want to do on start is think set um I actually have no idea. Over here we set load the first product directly into accumulator. Count. Guess we don't really need to do any of that control logic because that should be handled by the neurons individually. Um, Here, let's just if I guess not done, begin, then um, do we really need to do anything? Because the wires are all, oh, right, we need to load in the correct X and W values. So, X, guess we should probably keep accounts of how many like inputs we've iterated through. So there's that. And then X value is equal to X Then we want to slice this to be um oh, I guess we should probably add if start again, so count equals 1, right, x value equal to x from not 15 and that'd be m times 16, m times 16 minus 1 to 0. I forgot to semicolon. Here, then the weight value equal to the weight matrix. Then we would want to slice that. So how's this is how our weight matrix is arranged. So what we'd want to do is go from 0, bit 0 to bit m times 16. Yes, because there are m weights for each input. M times, wait, no, that doesn't make sense. There should only be one input, right? Yeah, so that'd be just 15, 15 to 0. And then weight would be that. And then B is already, the bias is already set. And I think that's the only thing we have to um, do. And then we can do and else if, oh, uh, forgot the semicolon. Done is equal to and is equal to 1. Again, we're just handling the edge case of single elements. So then count is greater than 0, which it should always be, and count is less than n, the number of inputs, then x value, so x is equal to um, count times 16. Wait, no. Count plus 1 times 16 minus 1 to uh, count times 16. This is incorrect. Then this is equal to weights So for every count, we would add m to the bottom, right? And the top. So really we can think of this as times 1, and then we can think of this as count plus 1 times m times 16 minus 1, what? Minus 1 count times m times 16. I don't remember if, let's figure this out. So, um, going off this situation again, n is equal to 2, m is equal to 2. In this case, on the second, when we're loading the second input, so x is equal to, we would expect this to be 16 bits. So that's count plus 1 times 16. 1. So in this case, counts is 1. That's 2 times 16 bits times 1, because that's how many inputs we load in. And then we subtract 1 to count, to just count 1. Wait, no, we start from count 1. Is that true? No, that's not true. So this would be 1 times 16 is 1, which of course just comes to 16. So this is equal to 31 to 16. I mean, that looks like 15 bits. It's probably, that's how I have all my other slices. That's how all my other slices work. So I'm just gonna assume that's working. And the weight, on the other hand, this should be m times 16 bits. So count. Let me just count is equal to 1. Yeah, because once count is equal to 1, if m is equal to 2, sorry, n is equal to 2, then this is no longer true. And we would move on to the next condition. So that is a scary bunch of parentheses. So that's 2 counts plus 1 plus 2, sorry, times 2m times 16 minus 1 to count times m times 16. 1 times 2 times 16. This is equal to 4 times 16, 64, 63 to 32. That looks correct. Okay. Now we would set count equal to count plus 1, and then, wait, do I even have it done while completed? Yes, I do. Done is equal to count is equal to n minus 1. So then we'd end this, and else if done again, done is equal to 0. And so now, once we're done all that, then the all the activations should be present. I'm not gonna test this because it's like really late and I can't be bothered. Thank you for watching. Follow me on Twitter. Let me just type it here at MITAV Krishna. The lack of an I there is intentional. Well, not really intentional. Some other guy has Amitav Krishna with an I. So, yeah, goodbye.